Hi everybody, welcome to our first exams review for dynamics. I did post something earlier on YouTube, but there was some sound difficulty, so I thought I would just go ahead and redo it. So bear with me through this. Hopefully I'm able to cover as much as I did the last time. I'm going to try to stay as consistent as I was the last time. All right, so for dynamics, what we've done so far is we've worked on two chapters. We've worked on chapters 12 and 13 of the book, if you do have it. And for our exam, we're going to be going over particle kinematics, which I'll talk about in just a bit, and then also partial part of what we've done in under kinetics. So for our class right now, we've looked at kinematics, which is basically dealing with geometrical aspects of motion. So in terms of motion, we know that there's some kind of direction and some kind of magnitude, right? So we're going to be dealing with some kind of the geometry of those kind of motions. And then we'll delve into kinetics, which actually deals with the forces that cause the motion. So you can see that there is a direct relationship between kinematics and kinetics. They're all not crazy new concepts. And what you want to pay attention to for kinematics is not worry about the force, but deal more with the actual motion that's happening. And then in kinetics, you want to deal more with the forces that are causing the motion. So what we're going to cover for the exam is continuous and erratic rectilinear motion, rectangular coordinates, and projectile motion. I put them to side by side because they are actually very related, and I'll talk about that in just a bit. And then we have normal and tangential coordinates and the cylindrical or polar coordinates. And you can see that there's some kind of repeat, right? If you're looking here, you're actually moving from kinematics to kinetics. You see that they are related, and the next three sections do repeat, which is really cool. So that means that you're not learning anything new under particle kinetics, but you're just dealing with how to apply your motion aspect that you got under kinematics into the kinetic side of things. All right, so what have we done so far? And what I thought I would do is actually just go over some of the exam equations that I have posted. This was compiled by Dr. Fons, and I just thought that we'll just quickly go through a few of the concepts. So under continuous and erratic, like the rectilinear motion or motion in the curve, things are really very similar to what we've done in physics and partially what we've done um, in our class as well. So when you have velocity, we know that velocity, acceleration, and displacement are very much related to each other. So in case you want to find your velocity, all you need to do is find the derivative, first derivative of displacement, and you should be able to find velocity. And remember that velocity is a vector, so it has magnitude and it also has direction. And then moving on to acceleration, we can see that if you find the first derivative of velocity, you should be able to get your acceleration, or you can find the second derivative of displacement, which is basically the first derivative of displacement is velocity, and then you can find the derivative again to be able to find your acceleration. Now, working forward or back, whether you want to integrate or you want to find the derivative, you should be able to move back and forth between each one of the concepts. So for example, if you have velocity and you want to find displacement, all you want to do is find the integral of velocity. So displacement is equal to the integral of velocity with respect to time, and so forth and so on. Now, this works very well for equations, right? If you have equations, you're gonna have to use either derivative or integral to be able to solve for problems like that. And that's very different from when you have constant acceleration or a single magnitude of acceleration. This is when you use the equations that are written down over here. The 5 equations are written down here. The biggest error I've seen so far in the class for dynamics is when a lot of you guys are kind of confused between using the standard equations of motion, which you're seeing over here, whether you want to find velocity or acceleration or displacement. It only works for constant acceleration. So if you have a magnitude, a single acceleration, you can just plug in here and find your velocity or displacement or any other component at a particular time. This does not work for when you have an equation for either acceleration, displacement, or velocity, and you're trying to plug it into here. That does not work. This works at assumption that said that there is a constant acceleration. So you want to go ahead and pay attention to that. Now, over here on the side is a really nice help to be able to help you out figure out which equations you want to use. So for example, if you don't have any displacement at all, so no s, and you want to find your velocity or constant acceleration depending on what you're looking for, you can go ahead and use equation 1. So if you don't have velocity, you can use equation 2, and so forth and so on. Just knowing what you have in terms of your givens and what you're looking for really helps you figure out if you want to go between equations 1 and 5. And that helps you in terms of all kinds of motion. So if you're given a problem where you want to find out the velocity at a certain point, whether it's from rest or not, depending on the kind of input you have or the givens you have. If you have constant acceleration, this part of the equation sheet is very nice and very handy. But if you don't have constant acceleration, you have some kind of equation, please consider using an integral or a derivative to be able to work between getting your displacement, velocity, or accelerations. All right, so moving on to rectangular coordinates. So basically, any kind of motion that we have, and if you went through statics, you are very conversant with this, that if you have some kind of motion, so let's say this this particle is moving along some kind of path, right? So if you look at it in terms of your simple x and y coordinate system, you can see that this particle moving in a curve can be resolved into its x component and y component, right? So for example, if you have your velocity, you could break up velocity into x, y, and z as needed, right? By saying that if you have your velocity in the x direction, sometimes we call it v at I, right? And then in the y direction, it'll be v at j. And then in the z direction, you have v at k. So you should be able to break up velocity into its components because velocity or acceleration, depending, are vectors, and you should be able to break them up, right? So when you have displacement in the x direction, y direction, or z direction, you can find the derivative of it to be able to get velocity at x, velocity at y, and velocity at z. In the same way, acceleration can be broken up into the individual components. So if you want to get the magnitude of velocity, what you want to do is find the square root of the square of velocity in the x direction, velocity in the y direction, and velocity in the z direction. And the same way with acceleration. And that's going to be the magnitude that you're looking for. That's kind of nice to have. So in the same way, looking back up here, when you're trying to find velocity, acceleration, and whether it's a constant acceleration or not, you can break it up into rectangular coordinates, which is just break it up into your simple Cartesian coordinates that you're used to, x, y, and z as needed, right? Or be able to break it into some kind of components, be able to use it. So in the same way, something that's very related to rectangular coordinates is when you have projectile motion, which is basically rectangular coordinates, but for a system that's in free fall. Now, a very important thing about projectile motion is that if you're thinking about free fall, which means that naturally things are going to want to go down, right? We're dealing a lot with gravity. So even though we are talking about kinematics at this point, we've not really delved into kinetics, which deals more with forces. You have to pay attention to one extra thing that's affecting your acceleration or velocity as needed, and that's the effect of gravity, right? That's not something that we can actually control. We always, whatever you throw up is going to come down at some point. So if you're dealing with some kind of projectile motion where something moves up and then eventually the effect of gravity tries to bring it down, you want to consider gravity in your equations as well. So for x direction, we have your acceleration in the x direction basically going towards 0, but your acceleration in the y direction, because it's going to be falling, is going to be in the negative, so negative 9.81 meters per second squared, or 32.2 feet per second squared. So that's the only difference between projectile motion and rectangular coordinates. And you can notice that you do have things in the x and y direction or z direction as needed, because in the end, everything has to be able to be broken up into different coordinate systems, which in this case, we're just using the normal Cartesian, which is x, y, and z coordinates. So nothing different from what we've done before, but now we're just delving into looking at the different coordinates of the same acceleration that we just worked on over here. Now, moving on to normal and tangential coordinates, which are very much similar to how your rectangular coordinates and projectile motion works. So normal and tangential coordinates, what that does is just basically looking at the same coordinate system that we looked at before, right up here, where you have a particle moving along a certain path, and we just be able to resolve them into our traditional X and Y coordinate system. But there are times where it's much easier to be able to put it in a different coordinate system than what we're actually traditionally used to. So when you have a material, some kind of particle that's moving in some kind of curve, and you can see that the material, the particle is kind of moving with its own coordinate system. What you can do is that you can come up with a coordinate system that alters itself while your particle is moving. So you have something that's tangent to your particle's path, or you have something that's normal. So as we are all very aware of, normal just basically means that you're 90 degrees, right? But if you look at some kind of reference curve in terms of its curvature, that you're normal to that point. You are 90 degrees to that point. And then we also have tangent, which just means you're in line with, for example, of that point. Now, what's different about this coordinate system is that as you're moving, what is normal and what's tangential does change, right? Because of how what path, according to the path where you're actually moving. So that's why you're not dealing with the traditional coordinate system, because your path, your particles actually moving all over the place in a path, versus the normal, the rectangular ones, where it's just basically at a certain point. So we have those two. So your remember, we have two components that we look at. We look at tangential, and then we also look at normal. Now, when the particle travels on a known path, a certain path that we are aware of, where the path has an equation, then you know that there's some kind of radius of curvature, which we call rho, right? Because if anything is moving along a certain path or some kind of curve, it's always going to have a radius around which it's moving that we call rho. So if you find that we have an equation given to you for rho, which is your radius of curvature, as soon as you have that, you should be able to find your normal and tangential accelerations pretty quickly by either tangential, which is just your velocity that's changing, right? Your speed is changing. So you find the derivative of that with respect to time, or you can use that velocity according to your radius of curvature to be able to figure out what's actually changing your direction. That's what's making your your particle move in a different direction along that path. And then finally, we have cylindrical coordinates, which basically is kind of similar to how normal and tangential coordinates work. And we're looking at radial and transverse directions. So once again, things that are moving in the direction of the origin, right, moving radially from the particle to its center of origin, or you have a transverse, which is what's going to make it actually want to rotate. So think about cylinder, which means it's something that's in 3D, and typically, and these are the equations that you want to look at. So for any kind of particle that's moving along some kind of curve, if you have your coordinate system, right, and your center, your axis of origin, looking at where the particle is available, you could say that this is a radial direction, r, right, moving from your origin to where the point is at, and there's an angle, that's theta. So there's some kind of rotation from the horizontal to where you are, for example. So if you want to go ahead and extend it out, that radial distance, you can see that there is some kind of radial direction that you're moving, which we call u sub r. And then there's some kind of rotation, which is going to make it, well, it's obviously tangent to where we are looking at. That's going to be u sub theta. Okay, so we're going to be looking at transverse direction, what's going to make it actually want to rotate, and we look at it in terms of counterclockwise, 90 degrees from where your radial distance is, right? So wherever your radial distance, which is a projection of your center of origin to where the particle is, and then if you rotate it 90 degrees towards counterclockwise, you should be able to get your transverse direction as well. Once you have that concept in mind, you know that you can break apart your velocity into radial and transverse directions. Remember that this is um, if you have theta, that's kind of angle, so you want to keep that in mind. And then you can also transfer it into acceleration by um, using the equations that we have in front of you, which is r double dot minus r times theta dot square. So everything is with respect to time. Okay, so going back up here to look at what we have at the top. This one has to do with traditional velocity equals derivative with respect to time of displacement. Acceleration is equal to the second derivative of displacement with respect to time, or derivative of velocity with respect to time. Under the next three, what you're looking at is the fact that all your velocity, acceleration, and everything else depends on some kind of Cartesian coordinate system, because velocity is made up of more than just a magnitude but in the direction in which you're going, which means you have some kind of Cartesian system. So under rectangular coordinates or projectile motion, you're dealing with your traditional x and y and z coordinate system. And then under projectile motion, you want to make sure that you pay attention. Sorry, that's just about projectile. You want to make sure that you pay attention to the effect of gravity. But outside that, the equations kind of remain kind of similar. You want to break things up into your x, y, and z coordinates. Your normal and tangential coordinates is making sure that you have the direction. So remember that when you're dealing with normal and tangential, you have a path in which the particle is moving in, but the direction of which the particle is moving keeps changing. So you're changing your coordinate system to match that. So you're dealing with your acceleration or velocity with respect to your normal direction and then also your tangential. And remember, tangent just means in the same direction. So if you have a path, a particle moving around the path, you have tangential, which means you're going tangent to the curve, right? And then normal, which means you're going 90 degrees to the curve. And then finally, cylindrical coordinates, which I just talked about. What you want to pay attention is to if you have a curve that you're based on your radial distance, which goes from 0 or your origin to where your particle is, which is at theta, your radial distance, you want to go ahead and project it. So then you have the component of the particle's position and velocity and acceleration, which is going to be a sub r. And then 90 degrees to that counterclockwise is going to be a sub theta. So now, as mentioned earlier, rectangular coordinates, normal and tangential or cylindrical, is pretty much the same as what we've done for kinetics. The only thing we're looking at that's different right now is that we are looking at the effect of force on those concepts. So coming back to our equations over here, we see that if you have a normal rectangular coordinate system, remember that from statics, we had sum of forces equals 0. But actually, what we were looking at was sum of forces equals m times a, where your acceleration was equal to 0 because your structure or whatever you're looking at was not 0, was 0. So in this case, we are not making that assumption because your accelerations, if you're looking at from kinematic side of things, actually are valid. Your particle is moving or your member is moving. So that's the only difference between kinematics and kinetics, and the difference between the entire class of dynamics is from statics. So you want to be able to use the original equations from Newton's laws, which said that sum of forces is equal to mass times the acceleration at which it's moving. So if you're looking at things in the x direction, we have sum of forces in the x equals m times acceleration in the x only. Sum of forces in the y equals m times acceleration in the y only. Guess what? We already found this based on kinematics. That's nothing new. So going back here to rectangular coordinates, you see that you have ax, ay, az, which is related to displacement and velocity at the different coordinate systems that we are looking at. So finding these ax and ay is actually something that we're very conversant with, right? If you're looking at normal and tangential coordinates, which we just talked about as well, summing forces in the tangential is equal to m times a tangential, which we found up here, and that's equal to the change in speed. So we have m equals to the derivative of speed. And the same way, f of normal is equal to m times a of normal, the acceleration in normal direction, and that's equal to mv squared over rho. Finally, in the same way, if you're looking at your uh, your cylindrical coordinate system, we have them right here, whether in 2D or 3D. Now, the only thing that's left that I've not talked about is when you're in the cylindrical coordinate system, there might be another geometry that you want to pay attention to. So going back to this drawing that I had over here, you see that we have the same drawing, right, from your origin to the path or the particle in the path, exactly the point at which we're looking at. You see that there is an angle theta, but only thing that we left out was your tangent line. So wherever you are, that angle between your radial distance and your tangent section, which we call t, is equal to phi, right? So coming back here, you see that tan of phi, which is the angle between your radial distance and your transverse direction, is equal to radial distance divided by the slope between your radial distance and the slope, which you have over here. So these equations are given to you, right? And all I need you to do is just be able to not freak out in an exam. Read the question very carefully. You have all these equations given to you. What we want to know is if you're able to apply the concepts into what you're doing. Are we dealing with something that has constant acceleration where we don't have to worry about the coordinate system, so all you're doing is just plugging and chugging? Or do you have some kind of vector that you're either in the xy coordinate system or x, y, and z, or you have some kind of curved path where you can deal in terms of breaking things into normal or tangential coordinates, or maybe cylindrical coordinates if you're in a 3D system, for example. You have a lot of examples that have been given to you. All your homework solutions have been posted, a lot of class notes. I'm going to try to find even more videos as needed if you want that as well. So hopefully this has been able to clear up a few things for you. In terms of this class, it's nothing difficult. If you're able to master the first part, which is particle kinematics, you should be able to plug that theory back into kinetics, which just basically deals with sum of forces equals mass times the acceleration or velocity as needed that you found in the kinematics section.